Alright, welcome back to homework 4 for Process Dynamics Controls. Today we're going to be completing the first part of part C of this homework, and what we're going to be doing today is we're going to draw and explain the block diagram for the Smith predictor control system for a closed loop system with dead time. So, getting started here, we've got, as we've had in many of our different block diagrams, we've got our GP, which is our control for our process, which is, I'm going to put this somewhere more towards the middle here. Here we've got our GP. That's going to be represented by our Kc times e to the minus theta s all over our tau s plus 1, our system with dead time, as we've talked about previously. Then, of course, we're going to have our GC for our controller. But for our system with dead time, what we're going to want a sort of model to predict what our process is going to look like, because we're going to have that dead time. We're going to want something to see what our process looks like in the meantime when we don't quite know. So we're going to need our model. And what we're going to call our model is we're going to call this GP bar. This is going to represent our model here. And our GP bar is also going to need a predictor for its dead time. So we're going to have a model dead time of our e to the minus theta bar times s. And of course, way down the line, our final y coming out. And then coming in to our GC, we of course have our set point, our y SP, going into our controller. Coming in here. And then we've also said that for our system with dead time, we might have a disturbance. So we might have a GD with a D, our disturbance, coming in here. We'll say that just comes in right here. And that disturbance is going to influence our y that's coming out here. What's also going to influence this is our model here. So we know we're going to have our model coming out to a comparator, something that's going to compare how our set point, or how our model compares to the actual process that we've predicted here. And then we're going to come all the way back around, right in front of our set point here. We're going to have another controller that controls based on how our model compared to what was actually coming out of the system here, so that we can potentially update our model. So what we've got right here is essentially the overall block diagram for our Smith predictor. Moving on, what we're going to do is we're going to simplify this down so that we can derive an actual analytical expression for a Smith predictor controller. So moving on to the next part of part C, we're going to go ahead and simplify this down and get an expression. So let's move on to that part. Right, now that we've got our overall Smith predictor block diagram, we can do a couple simplifications to this in order to get a an expression for the closed loop response of that Smith predictor control system to changes in both the set point as well as disturbances that might appear in our system. And the first simplification I'm going to make here is we can see we've got this closed loop right here. We can kind of combine our model and our model dead time into one expression, a loop that would look something like this. So we've got our set point coming in, first controller, going into another controller, and then we can go into our GC here. Then coming out of our GC, we can go ahead and combine these two in order to get one single closed loop expression of our GP bar times 1 minus r e to the minus theta bar s. Coming back up into here. And then that's all going into our process function. Of course, we've got our disturbance into our disturbance function. Coming up to here. Then another simplification we can make is we can just condense this entire closed loop down into one single closed loop transfer function. What that is going to give us, so we're going to have our set point coming in, our YSP, going into our initial controller. And that is going to come into this combined function right here, which is going to be our GC divided by 1 plus our GP bar times our GC times R1 minus e to the theta bar, negative theta bar s as our overall closed loop transfer function. Then we're still going to be going into our actual GP. And of course, we've still got our disturbance coming into our GD. So we're going to add to our total result. So Y coming in. There. Now that we have all of these functions put together into a single closed loop like this, what we're going to be able to do is we can combine these as we have previously with our block diagrams. First, combining in our GP, what we're going to get is that our Y going to equal our GP and our GC divided by our 1 plus our GP bar times GC times our 1 minus e to the theta bar s times our YSB. And to simplify this down, because we're also going to need to include our disturbance as well as our actual process, so we're going to call this entire transfer function here our alpha, and then combining in our disturbance, we get that our y is going to need to equal our gd times our d plus our alpha times our y sp minus our y. And then if we rearrange this and solve for y, we get our overall closed loop response function of y equals gd times our d. So I'm struggling with my algebra a little bit. All over 1 plus alpha plus r ysp all over 1 plus alpha. And right there is our overall function for our closed loop Smith predictor control system. So now we can move on to Python and do a little bit of simulating to simulate this out. All right, one small correction here. We are also, close that parentheses for one, we're also going to have an alpha up top next to this y set point, which it's still multiplying this out, but we're going to rearrange to say our alpha over 1 plus alpha times our y set point. That is our actual expression. So now we're good to go ahead and move on to the coding portion. All right, welcome back to the last part of homework for part C. We're going to go ahead and simulate the closed loop response of a first order system with a gain of 1, a time constant of 2, and a dead time of 10.5 seconds using an imperfect Smith predictor model with a gain for the model of 0.95, a time constant of 2.2, and a dead time of 10 seconds. We're going to compare the response of the closed loop system without that dead time compensation, so effectively without our model. We're just going to see what happens if we just run our system without any kind of model, and then we're going to compare that to our system using our Smith predictor model. And in both of those cases, we're going to use a controller. It's a PI controller with a controller gain of 5 and a reset time of 10. So as you can see here, we have a lot of constants that need to be initially put into our system here. So we'll get started with this first one. We know we have a K of 1. This is, of course, our gain. We have a time constant tau equal to 2. That is, of course, our time constant. We also have a dead time theta equal to 10.5. That is our dead time for our actual system. This is going a little bit out of order from how the problem presents it, but I like to put the KC right under the K just because they kind of look similar. So I'm going to say that our KC, we know that our controller gain is going to equal 5. So that's our controller gain. And then I'll also go ahead and just put the reset time right below here. So I'm going to say our tau I is going to be equal to 10. Our reset time. And then going down from here, going down the list of constants we need, we're going to need our model gain, which we're going to call K bar. That's going to be equal to 0.95. It's our model gain. We're going to need a model time constant, so we're going to call that tau bar. And that's going to equal to 0.2. 2, I believe. Yep. So that's going to be our model time constant. And then we're also going to need our model dead time, so our theta bar. And that is going to be equal to our 10 seconds. That's going to be our model dead time. And looking through our problems, I believe that is all of the constants that we're going to need to write this code. So I think we're good to go ahead and put in our GP, our actual process transfer function, because we're also going to have a simulated process transfer function right below this. But we know that our GP, that's going to be our K times our, put this in parentheses, our K times our e to the power of negative theta times s, our dead time right there, all divided by r tau times s plus 1. Perfect. And then we know that our GP bar, which is going to be our simulation process transfer function, that is just going to be equal to our K bar divided by our tau times s plus 1. So now we have both our simulated process transfer function as well as our actual process transfer function right above here. So the last of these functions we're going to need to do our initial simulation without our compensation is going to be our GC, which is of course our controller, our actual controller transfer function. And as we discussed up above here, we're going to be using a PI controller. So we know that for our PI controller, we've got our KC times R1 plus 1 divided by our tau I times S. And that, of course, is our controller gain and reset time. So I believe that should be just about everything to simulate our initial closed loop system without our dead time compensation provided by that Smith predictor model. So to do that, I'm going to go ahead and say our fig equals make subplots. Fantastic. And we're going to do fig dot, I forgot completely that we can't make our figure without first simulating this system. So we, of course, are going to need our t and our y, and those are going to be equal to our simulation of our big function we figured out up on the board there. So that's going to be our GC times our GP. I'm going to put that in parentheses for us. All divided by R1 plus GC times GP. Uh-oh, what's going on here? Sorry, parentheses are getting kind of funky. And then, of course, we need our lambda. Lambda t. Lambda t. 1. We're going to have our n equal 1,000. And then I'm going to have our dt equal just 1 this time. Or we'll start with 0.1. We'll bump it up to 1 if we need to. Fantastic. And now we're good to go ahead and make our subplot. So you can say fig equals make underscore subplots. And we do fig dot add scatter. And then our x, of course, is going to equal our t. Our y is going to equal our y. And our name is going to be our closed loop system, no dead time. Or I'll just make it the name. It doesn't need to be the title. No dead time compensation. Shift enter here. So it's a little hard to tell here, which is why I said I think I might want to increase our dt a little bit, but you can see we never really find a stable y here. We kind of just oscillate, we kind of just go straight up and start coming straight back down because there's no compensation for that dead time. So let's say I made our dt up to here. Like as you can see here, we are just going way up into 10 to the 66. This is never stabilizing, never becoming stable. This is a completely unstable graph. So we're going to need to use our Smith predictor model to model our process before we go in and actually try to control our process. And we're going to do that with our Smith predictor right below here so we can compare that graph to what we're seeing up here. So to get started here, as we were talking about up on the board when we were defining our function for our Smith predictor model, we're going to need an alpha, as it's just going to make everything a little bit easier in terms of the equation. So our alpha, we said up on the board, is going to be equal to our GC times our GP, all divided by our 1 plus our GC times our GP bar times 1 minus our e to the power of our negative theta bar times s. And that was our alpha value we defined up above. What we're also going to need besides that alpha value is we're going to need our GD, which is going to be our controller for our disturbance that we see in our system. So we're going to call it our GD. We're just going to say that our GD is equal to our GP for now because we don't really have a function for that. So that should be all good. And then we can go ahead and say that our t and our y is equal to the simulation of our GD. Forgot we need to simulate the two parts of that function separately. So as we described it before, we kind of separated it into two parts divided by our 1 plus our alpha. So we're going to say our t and our y disturbed, which is going to be our change in our disturbance. That's going to equal the simulation of our GD divided by our 1 plus our alpha. Again, we're going to need our lambda, the T1, our N equals 1000, our DT equal to 0.1. Fantastic. And then we can see our T and then our Y SP, our Y set point, is going to equal to our simulation of our alpha divided by our 1 plus alpha. And those are just those two different additions of the overall function we derived up on the board earlier so that we can get our overall function for our Smith predictor. Just put the rest of our stuff in here. dt equals 0.1. Fantastic. And now we're going to go ahead and plot these out so we can compare them to our model without the dead time compensation. So we're going to again say fig equals make subplots. Do fig dot add scatter. Our x is going to equal t. Our y is going to equal y disturb. And our name is going to be our disturbance. What am I missing here? Oh, there we go. And then, of course, do fig dot add scatter. Our x is again going to equal our t. Our y this time is going to equal our ysp, and our name is going to be our set point. I think that should be all good. I'll go ahead and hit a shift enter. And that is just perfect. As you can see, now that we have that predictor integrated into our control system, as we get these changes in set point and our disturbance, they kind of interact with each other to keep the system completely stable. Every time there's a jump or something like that, you see the other one respond. And what this allows us to stay stable throughout longer time scales. Whereas, as you can see here, this system, once you hit your dead time, just flies. It becomes completely unstable and flies way out of range. And I think that is the end of our homework for part C. So I'll see you in part D.